This next section is on the properties of logarithms. So we're going to continue with logarithms, and we're going to look at doing some operations with logarithms and how those properties work. So let's remember at the top of your notes it says definition of a logarithm. It says the log base a of x equals y means that the base a raised to the y power, this represents the exponent, is equal to x. Common logarithms are logarithms in base 10, and we write just log instead of log base 10. If you just see log, that means it implies base 10, so you don't have to write it like that. Natural logarithms, remember, are logarithms base e, and we write ln, which means log base e. You wouldn't see it written that way. This is the acceptable way. So let's look at the properties. We're going to start with one called the product rule, which you had product rule when you were doing exponents. So this is similar. And here's what it says. The log base b of m times n is equal to the log base b of m plus the log base b of n. And just for a second, let's go up here and let's kind of remember how the product rule worked for exponents. It says if you have a base raised to a power times that same base to another power, that it's b to the m plus n. So you can see here that multiplication of like bases and addition of exponents is related, and that's what you're seeing in this log property, the product rule. Now you have to note there's a couple things it doesn't equal, and it's tempting to do this, so you have to be sure that you understand what that looks like. So let's look again. The log base b of m times n, here's what it doesn't equal. It's not the log base b of m plus n. That doesn't make sense. It is also not equal to log base b of m times log base b of n. You're not distributing that. It's related to your exponential product rule. So don't get confused. These two are what it is not, but this is what it is. Okay? I'm not trying to confuse you, but I might as well just point out what some people are going to do to begin with, so maybe you won't do that and you can avoid that mistake. Let's look at the quotient rule for logs. And we have the log base b of m over n. Now again, think about what it was for exponents. It would be the base to the m minus n, right? It's exactly related here. It's the log base b of m minus the log base b of n. Again, here is what it is not. Let's do m over m. It's not equal to the log base b of m minus n, like that. That doesn't make sense. But it's also not equal to the log base b of m divided by. It's not a distributive property. So again, these are what it is not. This is what it is. Finally, we have the power rule for logs. So let's take a look at it. It says the log base b of m to the r power. This one's easy. You just bring that r to the front. It's r log base b of m. That's a pretty easy one. So let's look at how we use these. Example 1, it says write log base b of x times square root of x squared plus 1, with x being greater than 0, as a sum of logarithms. Express all powers as factors. So let's start breaking it down using 1, 2, 3. Those three rules. So here we go. Log base b of x times square root of x squared plus 1. First off, I notice I'm taking the log of two things that are multiplied together, so I'm thinking product rule. So I'm going to say that's equal to the log base b of x plus the log base b of x squared plus 1, radical x squared plus 1. Now right underneath that, this I can't simplify, so I'm going to write log base b of x plus, but another way to write this is log base b of x squared plus 1 to the 1/2. And we know from our power rule that I can take this and bring it down in the front. So what I have is log base b of x plus 1/2 log base b of x squared plus 1. And it's been simplified. Alright, let's look at example 2. It says write ln of x squared over x minus 1 cubed as a difference of logs. And here we know that x must be greater than 1 so that we don't have 0 in the denominator. Express all powers as factors. So let's start. I am dividing, so I'm thinking quotient rule. So I'm going to say that is ln of x squared minus ln of x minus 1 to the 3rd power. Now I'm thinking power rule because I have an exponent. We're going to bring it down in front to ln of x minus 3 ln of x minus 1. And you have it. That one was actually easier than the last one. All right, let's look at example 3. Here we have log base a of radical x squared plus 1 over x cubed x plus 1 to the 4th. Again, x is greater than 0. We can't have a 0 in the denominator. Now this one has a lot of steps because there's a lot going on here, but if you look kind of at the big picture first, what I see is the quotient property. I see a division, so I'm going to write that first. I'm going to write that as log base a of x squared plus 1 radical minus log base a of x cubed times x1 to the 4th. So all I did was split that division into a subtraction like this. Now I'm going to do some other changes. We know not to show that as a radical, but instead as a rational exponent. So that gives me log base a of x squared plus 1 to the 1/2 minus, I'm just going to recopy this one at this point, log base a of x cubed x plus 1 to the 4th. Now I know that I can take this and bring it down front, so that would give me 1/2 log base a of x squared plus 1. I think that's all I can do with that one. Minus, now notice what I have here. I have log base a, and then I have two things being multiplied, x cubed and x plus 1 to the 4th. So I know I can split that using the product rule. So what I have, I'm going to move over here, is 1/2 log base a of x squared plus 1. I'm just recopying that. Minus, now in these brackets, I'm going to apply my product rule. Log base a of x cubed plus, that's the multiplication and the product rule, log base a of x plus 1 to the 4th. And we are getting there. So now I can bring this down front and this down front by the power rule. So I've got 1/2 log base a of x squared plus 1 minus, keep this in brackets, 3 log base a of x plus 4 log base a of x plus 1. And now there's only one step left. I'm going to distribute that negative sign, the subtraction. So I have 1/2 log base a of x squared plus 1 minus 3 log base a of x minus 4 log base a of x plus 1. And I know you're probably thinking, why on earth would you ever do that? It looks so much nicer like this, because there's times where you have to understand what an equivalent expression of the original is. So let's look at example 4a. It says write each of the following as a single logarithm. So now we're going to take something like this answer and work our way back to it being a single log. So we have log base A of 7 plus 4 log base A of 3. So the first thing I'm going to do is take this 4 and move it back as an exponent. Log base A of 7 plus log base A of 3 to the 4th. 3 to the 4th I can actually multiply out. So I've got log base A of 7 plus log base A of 3 to the 4th is 81. So now I've got this plus of these two logs in the same base, so I can put it together in multiplication with the product rule. Log base A of 7 times 81, which is log base A of 567, and I put it back into 1, a single log. Let's look at B. I've got 2/3 ln of 8 minus ln of 3 to the 4th minus 8. First thing I'm going to do, I'm going to move that up to the exponent spot. So I've got ln of 8 to the 2/3 minus ln of, we can go ahead and multiply that out. That's 81 minus 8. So we have ln of 8 to the 2/3, we'll deal with that in just a second, minus ln of 73. Okay, now let's deal with 8 to the 2/3. 8 to the 2/3 means the cube root of 8 squared. Cube root of 8 is 2. 2 squared is 4. So what I have is ln of 4 minus ln of 73. Now this is subtraction, so I'm going to use my quotient rule, and I know that that means ln of 4 over 73, and I have it back as a single log. You just have to go one step at a time on these and not get lost. All right, here we have log base A of x plus log base A of 9 plus log base A of x squared plus 1 minus log base A of 5. All right, let's just take these first two terms. There's a plus there, so I know that's my product rule. So I'm going to write log base A of 9x. Now I'm going to recopy the rest, plus log base A. I'm not trying to do it all in one step. I'm doing one step at a time. Okay, so I took care of those two. Now let's look at these two. There's a subtraction there. So I know that that is a division situation, or you can think of it that way. I can think of taking care of these two. So it kind of just depends on which you want to do first. It should come out the same. I'm going to take care of these first two first, so I keep it in order. So I got log base A of, I need to multiply those. 9x times x squared plus 1, and then I have minus log base A of 5. I'm actually not going to incorporate that minus until the very, very end. So let's simplify a little bit here by distributing that 9x, and we have log base A of 9x cubed plus 9x minus log base A of 5, and now I'm ready to put those last two together as a division, and that's going to give me log base A of 9x cubed plus 9x over 5, and I have it back to a single log. Okay, let's look at example 5. Here's some other properties of logs. It says show that log base A of 1 equals 0. Well, how would we do that? Let's let y equal log base A of 1. So if I take this, and I now convert that to exponential representation, I would start with my base A to the y power equals 1. But I know that 1, I could write A to the y power equals A to the 0. That's a 1, right? Now I have the same bases, so therefore I know that y here is equal to 0. So we just proved that log base A of 1 is equal to 0. So let's look at B. That was A, by the way. It says show that log base A of A equals 1. Well, again, let y equal log base A of A. Now write it exponentially. That would be A to the y equals A. So A to the y equals A to the 1. Same basis, therefore y equals 1. And remember what y was? Log base A of A equals 1. And we just proved that. So there are some conclusions at the bottom of that page. It says when base and result match. So when we have log base B of B, so this, the base, matches the result, that's equal to 1. So log of 10, remember that means log base 10 of 10 is 1. And ln of E is 1. That's why when we do that on a side of an equation, it cross cancels and makes a 1. They undo each other. Okay? So that's one conclusion. The second conclusion is when the result is 1. So if you have log base B of 1, that's equal to 0. So log base 10 of 1 is 0. And ln of 1 is 0. Alright, let's look at some inverse function properties on the next page. It says recall. F of f to the negative 1 of x is equal to x, and f to the negative 1 of x equals x. So we can say in the same way a to the log base A of m is equal to m. Notice it's the base, the same base, being raised to the log base A of m is m, and the log of A, base A, of A to the m is just m. So if m equals n, then we know that log base A of m equals log, you can take the log of both sides, and we know if the log base A of m equals the log base A of n, then the inverse is true. M equals n. Alright, let's look at example 6. Here we're going to approximate some logs where the base is not 10 or e. So it says approximate log base 2 of 7. So we're going to start out by saying let y equal log base 2 of 7. Now we're going to write that exponentially. So I'm going to write as exponent. Alright, so we're going to say the base 2 to the y equals 7. Now I'm going to take the ln of both sides, and using my power rule I can bring that y in front. Y times ln of 2, because that's what the exponent means, is ln of 7, and now y is equal to ln of 7, divide both sides by ln of 2. So y is approximately equal to 2.8074 if you put this in your calculator, and y was equal to what again? Log base 2 of 7. So we just approximated that. It's kind of strange. Alright, last thing on this set of log properties is the change of base formula. It says if a is not equal to 1 and b is not equal to 1 and a, b, and m are positive real numbers, then the log base A of m is equal to the log base b of m over log base b of a. Look at that carefully. And I can write it another way. Log base A of m is equal to ln of m. This is the way I would do it. Over ln of A. Look where that's coming from. We just showed that with example 6. So let's look at example 7a. It says approximate log base 5 of 89. Well, it should be approximately equal to the log base 10 of 89 over the log base 10 of 5. Put that in your calculator and you're going to see it's about 2.7889. Alright, let's do another one. Just have to memorize this formula. Log base 2, or square root of 2 of radical 5, which means log base radical 2 of 5 to the 1/2 should be, following this pattern, the log of 5 to the 1/2 over the log of 2 to the 1/2. This is 2 to the 1/2, remember. But I can bring those 1/2s out front, 1/2 log 2, and those make a 1, and I end up with log base 5 over log base 10 of 5 and log base 10 of 2, which is approximately equal to 2.3219. Kind of tricky, this change of base formula. Again, see the summary of properties of logs in your textbook on page 456.